Hi everyone. In continuation with our lecture series on the different sources of participation in CMOS inverters, in this lecture we will look at another important source of participation in a CMOS inverter. So, just to quickly refresh your memory, in a CMOS inverter, in the previous lecture we spoke about, we talked about the dynamic participation, which is what we said when your input is toggling, when your clock signal is toggling from 0 to 1 or 1 to 0, we said that a finite amount of charge is drawn from the supply. Mainly, the charge is not drawn from the supply for if the input is say going from 0 to 1, what would happen is that the NMOS will discharge the capacitor, and when the input goes from 1 to 0, the capacitor will be initially charged to 0 and the PMOS will charge it up to VDD. So when the PMOS is charging it, we said that the total charge that this load capacitor CL receives is CL into VDD, and this charge is delivered every t seconds. So the average current drawn will be CL into VDD by t multiplied by VDD is your dynamic participation. And we saw that this dynamic participation was dependent on 1 by t is your clock period times VDD square. Okay, so that was the dynamic participation, and we saw that it depends upon the voltage, frequency, and the load capacitance. Now, in this lecture, we will look at another source of participation, which cannot be accounted for in a dynamic part. So, to understand that, I'll very briefly first qualitatively try to understand what that source of participation is, and then we'll try to use some simple intuitive mathematics to draw some conclusions as to what it depends upon. Now, when your input goes from say 0 to 1 or 1 to 0, what would happen is, for example, let's say the input goes from 0 to 1. So which means previously the input was 0 and suddenly the input goes to 1. So which would mean at the output, when the input was 0, it would have been charged to VDD and the NMOS is supposed to discharge. So the instant, so when you have a step change in your input signal from say 0 to 1, previously PMOS was turned on when the input was 0, and suddenly when it goes to 1, your NMOS is turned on and PMOS is turned off. Okay, so when input goes to VDD, the PMOS's VGS goes to 0, instantly it is turned off and NMOS is turned off. And the output capacitor is discharged to 0. And similarly, when your input goes from 1 to 0, your NMOS is cut off and PMOS is turned on. But in reality, you don't have step inputs. Your inputs don't instantaneously go from 0 to 1, but rather they all have a finite rise time as shown here. So they would take a finite amount of time to go from 0 to 1. So therefore, you won't have this sudden transitioning of NMOS conduction to PMOS conduction. So when the input was going from 0 to 1, in this case, we saw that PMOS was conducting and suddenly at that instant, rising edge instant, NMOS began to conduct. But in reality, that's not the case because your input gracefully goes from 0 to VDD with some finite rise time. Now, because of which, there will be a brief interval when both the NMOS and the PMOS will be conducting, and you will have a direct current flowing from the supply to the ground. Remember, any current that flows into the capacitor, that goes into charging the capacitor, and we can account for the dynamic participation. Whether it's charging or discharging, if your current is going through the capacitor, then that is accounted for in the dynamic participation. What is not accounted for is that current which flows from VDD through PMOS and NMOS to ground. That was not accounted for in a dynamic participation. And this current, which flows from supply to ground, especially during these transition times when the switching happens from one device to another, there is a brief interval when both the devices will be conducting and a current will directly flow from supply to ground. It's like shorting supply to ground. So it's called the short circuit current, and this participation is also called the short circuit participation. Again, there are different words used in different books, so some books call it shoot through current. So, but the important thing is to understand that there is another different source of participation other than dynamic participation in a CMOS inverter. Now, shoot through current, as we saw intuitively, it depends upon the finite rise time, The rise time is finite. So for example, let's say we are switching from 1 to 0. So which means NMOS was initially conducting and then PMOS starts to conduct at the end of the transition. When we are switching from 1 to 0, the VGS of NMOS decreases and the VGS of PMOS increases. So initially it was VDD and the input is going from VDD to 0. So ideally, as the input is transitioning, you would want all the current in PMOS to charge this capacitor. But the PMOS will carry two components of current. One component of current will be going into the capacitor, another component will be flowing directly through the NMOS. So this current will have two components, ISC, the short circuit current which flows through NMOS, plus the dynamic current which is charging the capacitance. What we are interested in here is this current. So we have already accounted for the dynamic current when we spoke about the dynamic participation. So now we will look at how to quantify this and try to draw. I mean, I won't go much into the mathematics of it, but what we need to do is especially when the equations get complex, we rely on simulations, but we make some very simple approximations and derive some mathematical models that we can use for our understanding. It will definitely be very helpful in designing as well. So to understand this, we'll assume an input clock signal with a finite rise time. So the rise time of this, I'm going to call it TR. So that's the 100% rise time. So the time it takes for the clock signal to go from 0 to VDD. And for simplicity, I've assumed it's a constant slope. The slope is fixed. In reality, that will not be the case. It will have some change in the slope, but for mathematical convenience, I'm assuming the slope is constant. So the slope of this is given by VDD upon TR. So that's the relationship between slope and the rise time here. So as your input increases, say from 0, I'm talking about the transition going from 0 to VDD. Your output signal initially, because input was 0, it's already charged to VDD. So output is supposed to go, as your input goes from 0 to VDD, you would expect the output to go from VDD to 0. So as your input clock signal rises and it reaches, say, VTM, what would happen is the NMOS will start conducting. PMOS is already conducting, but the VGS of the PMOS has decreased a bit and NMOS starts conducting. Just when the input clock signal crosses VTM, NMOS device starts conducting. At that instant, the NMOS device will start conducting some current. PMOS will also, output is more or less charged to VDD. So PMOS is, remember when the input voltage is 0, PMOS already has a channel present, but there is no lateral electric field because your VDS has come to 0. But now, since your VGS is decreasing, NMOS is absorbing some current, there will be some IR drop across the PMOS. So therefore your VDD, the output voltage will slowly start decreasing. Okay, so some amount of current, that decrease in, NMOS will also absorb some current. Okay, but it will be a very small current and the voltage will slowly start decreasing. Now, as you increase your input signal further and further and further, the NMOS current starts increasing. PMOS current was already large to begin with. PMOS current starts decreasing. There will be one point when the PMOS current will become exactly equal to NMOS current. So see here, the NMOS current is increasing, PMOS's current is decreasing because its VGS is decreasing. So there will be one point where both these currents will match and the current flowing through the capacitor will be 0 at that point, only at that instant. So typically that point is your switching threshold. So for a CMOS inverter, if you recall a CMOS inverter characteristics, if you draw the line V0 equal to Vi, the point where it intersects is what we call the switching threshold. So that's the point after which you'd say that the output has started going below the input. Okay, so that's the point your output starts switching its state from, say, VDD to 0 in this example. After that, as your input signal increases further, what would happen is that the voltage would start choking the PMOS, and eventually, when you reach VDD minus mod VTP, the PMOS will be turned off, and from then onwards, NMOS will start discharging this capacitor fully. So this is what I've shown here. See, what I've shown here as a representation is the short circuit current. This is the current that flows both through NMOS and PMOS to ground, from supply to PMOS, then to NMOS to ground. And the point where it peaks, that's the point where NMOS current keeps increasing and PMOS current keeps decreasing. and they both become equal at this point, the point of switching threshold. So it starts at this point, so which is when your input signal crosses VTN, and then it ends when your input clock signal reaches VDD minus mod VDD. Okay, and in between it will reach a peak value, and that peak value usually happens to be at the switching threshold of the CMOS inverter. So at this time interval for which there is a finite current flowing from the supply to ground, I'm going to call it the short circuit time, TSC. Okay, so there is we can derive some very simple relationships between TSC and TR. TR is what we know, which is the rise time, is what we are aware of. So I'm going to call this voltage difference. So the voltage from VTN, when your input clock goes from VTN to VDD minus mod VTP, as delta V. So since the slope is same, I can say VDD by TR, which is the slope of this signal, should be equal to delta V upon TSC. Okay, delta V is the change in voltage, and that's the duration for which there is a short circuit current flowing from supply to ground. So we can say TSC can be written as delta V by VDD times TR. So I can say it's some alpha times TR, some reduced version, a scaled version of TR, but its alpha is less than 1. Obviously, because it's a smaller range of voltages we are concerned about. Delta V is smaller than VDD. So now if you see, the same thing would happen even at the falling edge. When your input is going from, say, VDD to 0, output has to be charged from 0 to VDD. A similar phenomenon would happen, and you would have a current, the short circuit current will increase as soon as you reach, say, this voltage is VDD minus mod VTP. So PMOS will start conducting, and this point is when NMOS stops conducting. So this will be VTN. Okay. So similarly, I can say that you'll be drawing a current during the falling edge as well. Whenever there is a finite transient, rise and fall times, you will end up drawing currents out of it. You will end up drawing current from the supply, which will directly go into the ground. Okay. So now, to estimate what is the average current, I'll just find the charge. The charge is simply, I've assumed a triangular model for the current. Because if I assume a linear ramp for voltage, assuming a square law device, the current waveform will be more parabolic in shape. We can carry out an exact analysis, but for simplicity, I've just assumed it to be a triangle. So the charge is simply the area under this graph, which is half base into height of this triangle. So half I peak into TSC, and you have two such triangles, in one cycle during rising edge, another during falling edge. So the total area will be, the total charge that you're going to draw from the supply is going to be I peak into TSC. The average current is charge drawn, so you're drawing this charge every cycle. Okay, the rate at which the charge is drawn will be your current. So I divide it by T, I get ISC. So this term I'm going to call TSC by T into I peak as the short circuit current. So since I said TSC can be written as alpha times TR, some fraction of TR, I can express this as alpha TR upon T times I peak. And in fact, 1 by T, you can further reduce this expression. And I'm sorry, I'll just erase this off. So I can write 1 by T as F clock. So the average current drawn from the supply, if you see, depends upon the peak value of this current, the rise time, and the clock frequency, F clock. That's your average short circuit current. So immediately, once you know the average current, you can find the average power drawn out of the supply. That will simply be VDD multiplied by this. So you'll have to just multiply VDD with this expression. So in fact, you can just pause the video and have a look at these expressions. I've also written the expression in terms of slope. Your slope is VDD by TR, which is also equal to delta V by TSC. I've written the expression in terms of all of that. You can just pause the video and probably look at it if you want to. Otherwise, we can directly look at the final result, which is this one. So the average current is simply alpha times TR times I peak times F clock. That's your average current. And you multiply it by VDD, you get the average short circuit power. Now this average short circuit power depends upon the rise time of the input signal, It depends upon the supply voltage and the clock frequency. And remember, it also depends upon this term called the I peak. So this is the current we said when your currents through both NMOS and PMOS devices become exactly equal and no current flows into the capacitor. And you can find that out by equating the two currents. So that point happens to be the switching threshold. If I make this assumption, beta n, which is mu n Cox W by L of NMOS equals beta p, which is mu p Cox W by L of PMOS. So I'm going to assume both of them to be equal, and I'll assume that VTN, the threshold voltages of the MOS and the PMOS, NMOS and the PMOS are the same. Then that voltage, the VGS of both these MOSFETs will be equal to VDD by 2. So using that, I can write the expression for the peak current as beta n by 2, which is the simple square law model, mu n Cox W by L2 into VGS minus VTN the whole square. So now we have an expression which shows the expression for the short circuit power dissipation, which shows its dependence on the various parameters. One, it has a direct dependence on the rise time. So if you have a larger rise time or a smaller slope, your short circuit current. So I'm always relating rise times with also slope. So your rise time, keep in mind, is a function of the slope as well. So alpha times TR is nothing but TSC. So that will depend upon delta V upon S. Okay. So delta V upon S, there is some dependence on slope. So if your TR is 0, your slope is infinity. So if you have a signal whose input signal slope is infinity, your short circuit power dissipation will be 0. So smaller the rise and fall times, smaller will be your short circuit power dissipation. The another thing, of course, they also depend upon the clock frequency, because every time there is an input clock transition, you are going to draw some charge. And if you increase your clock frequency, the frequency at which those rise and fall edge arrives will also be more. So you'll be drawing out more and more charge from the supply. The rate at which you'll be drawing from the supply will be higher. So more current, therefore more power. And finally, we will look at the threshold, the dependence on the supply voltage. So as I increase my supply voltage, we saw that in case of dynamic power dissipation, it was proportional to VDD square in case of dynamic power dissipation. And in case of short circuit power dissipation, it looks linear, but you should keep in mind the peak current also depends upon VDD by 2. Therefore, to a first order, assuming a square law device, we can say that it will have a cubic dependence on the supply voltage. If I increase my VDD by say 10%, you should expect nearly approximately a 30% variation in the short circuit current, assuming a square law device. Okay, so this term alpha is actually delta V upon VDD. So it has a weak dependence on VDD. So I'm still assuming it's more or less constant. It's more or less constant with the supply. So we can ignore that. Okay, so it'll have a cubic variation in supply, but if you assume a more complex mathematical model for your drain current, so then you'll have some nth power dependence on VDD for the short circuit power. So now going back to our first question, which we had asked previously, we said that in one of the cases, I was increasing my load capacitance. So mind you, when I change load capacitance, what did I mean in that question? The load capacitance of the CMOS inverter is an external capacitor. Okay, I'm not touching the device sizes of this MOSFET, of these MOSFETs. I'm just varying this load current, and I noticed that the power dissipation did not change. That cannot be true for a dynamic power, because dynamic power is directly proportional to load capacitance. So therefore, it could be that the dominant source of power dissipation in that inverter is a short circuit power dissipation, which doesn't have any dependence on the load capacitance. It actually has a dependence upon the W by L ratio through beta n, but that's the self-loading. So there is a weak dependence, but if I say that the load capacitance is an external load, this is purely the load offered by the next stages, then even if you change that, your short circuit current will more or less remain the same. Okay, so in the next lecture, we will look at another source of power dissipation in a CMOS inverter. Thank you.